So today we're gonna give a super brief history of elliptic integrals and elliptic functions. Elliptic integrals came from the computations of arc length, in particular arc length of ellipses. But not exclusively. Computation of arc lengths of other curves, for example the Leibniz gate, also lead to elliptic integrals. The arc length of this arc from the origin to the point corresponding to the radius r equals to a can be given by the following integral. And more generally, an elliptic integral is gonna be of the same form. Its integrand is gonna be some rational function of the variable t together with the square root of some cubic or quartic in t. What's special about these integrals is that they cannot be expressed as elementary functions. Thus, we can think of them as defining new transcendental functions. However, the first mathematicians who studied these were not thinking of them as functions. Their main interest was in finding addition theorems for these integrals. What are addition theorems? Well, they are laws of this form. However, Euler and Fagnano were not thinking of them in terms of this functional notation, rather they were thinking of them in terms of these upper limits of this integral. Euler showed that the upper limit here of this sum is just gonna depend on a and b algebraically. This is called Euler's algebraic addition theorem for elliptic integrals, and it says that the sum of any two arcs of a Leibniz gate is an arc whose parameter, c here, depends only algebraically on the parameter values of the original arcs. Later, we will see that there is a much more intuitive way to think about these addition theorems. We'll discuss that when we talk about contribution by Abel and Jacobi. But for now, let's talk about the first mathematician who studied these elliptic integrals from a functional viewpoint. That is the great Legendre. As mentioned, he viewed each of these integrals as a function of this upper limit. He was very excited about these new transcendental functions and spent a lot of his career studying and classifying them. He divided them into 3 types and also computed many tables of values for them. He was actually the one who came up with the name elliptic functions. He called these integrals elliptic functions. But be careful, these are not our modern day notion of elliptic functions. However, our modern day notion of elliptic functions do indeed come from elliptic integrals. It turns out that there is another way to generate new function from elliptic integrals. And that approach is much more fruitful than Legendre's. The way to do so is via inversion. This is the approach discovered by Abel and Jacobi, both independently. Instead of viewing E as a function of A, like Legendre, Jacobi and Abel viewed A as a function of E. In the case of the arc length of the unit circle, for example, from calculus we know that E is just arc sine of A, and so A is just sine of E. Thus these functions here are just generalization of the usual trig functions. Addition theorems, therefore, are just generalization of addition formulas for trig functions. Now we call these functions phi here elliptic functions. Thus elliptic functions are just inverses of elliptic integrals. This viewpoint turns out to be much more fruitful than Legendre's viewpoint. For example, the addition theorems allow us to compute special values of these elliptic functions and also to extend its domain. In particular, we could extend them to include complex numbers. And while the usual trig functions are only periodic with one period, these elliptic functions, when viewed as functions of complex variables, are actually doubly periodic on the complex plane. So they can be viewed as a function on a torus. Now the question is, how did Legendre miss out on this? With hindsight, inversion really seems like the most obvious thing to do. because that's the thing we naturally do with the trig functions. So how could someone like Legendre, someone who has spent so much time working on this, miss this? Well, Jacobi seems to think that's due to Legendre's discomfort with complex numbers. Back then, complex analysis was only in its infancy, and many mathematicians, Legendre included, were hesitant to work with complex numbers. Actually, even Jacobi and Abel themselves have some trouble. Let's see what their difficulty is. The issue is that when they extend the domain of this integral to include complex numbers, the integral suddenly become not well defined. This is because there are potentially many paths from 0 to a. Thus, this quote-unquote function here is gonna become multi-valued. And neither Abel nor Jacobi had enough tools yet to deal with multi-valued functions. It was Riemann who first found a good way to resolve multi-valuedness by introducing Riemann surfaces. Let's look at an example. How about let's look at the multi-value function square root of z. This is multi-value because every point in the complex plane has two square roots. To resolve that, we are gonna form a Riemann surface. We are gonna do so by taking two copies of the complex plane and then glue them along some branch cut. You can think of the result as looking somewhat like this, but not quite. In reality, the Riemann surface should be smooth everywhere, so this is only for purpose of visualization. Okay, let's come back. So we glue two copies of the complex plane along this slit, along this branch cut, and get a Riemann surface S. Now, we can fix the multi-valuedness of our map by replacing the domain with S. Now, when a point Z is moving in this first copy of the complex plane, our map is gonna map it to the first square root. When it enters the second copy of the complex plane through the slit, then the map is gonna map it to the second square root. Thus, our multi-value function becomes a single-valued function on the Riemann surface. Thus, we can view these elliptic functions as functions defined on Riemann surfaces. Actually, Riemann even generalizes the notion of elliptic functions to a larger class of functions on Riemann surfaces called abelian functions. So what are these abelian functions? Well, just like elliptic functions come from inverting elliptic integral, abelian functions come from inverting abelian integrals. These are generalization of elliptic integral, whereas the integrand of elliptic integral is a rational function in the variable t and the square root of some cubic or quartic polynomial in t. For abelian integral, the integrand is a rational function in t and some omega that is algebraically dependent on t. This elliptic integral just corresponds to the case when omega is the square root of pt. In other words, it corresponds to the case when this f here, this relation between t and omega, is just omega minus square root of pt. Now, there is a more modern way to define abelian integral. We could view them as integral of some differential one form from a fixed point p0. This can be viewed as function of p, but not taking value in the complex number because again, this is not well defined. We need to choose a path from p0 to p. So instead of viewing this as a map to C, we can view this as a map from the Riemann surface to its Jacobian. You can see our videos on periods to get more intuition about this map and its significance. So that's a super brief history of elliptic integrals and elliptic functions. Let us do a quick recap of the story. The problem of computing arc length leads to the study of elliptic integrals. Now, inverting these integrals leads to new functions. These functions are generalization of trig functions, and in particular, they also have addition laws. Using these addition laws, we can compute special values of this function and also extend them to complex numbers. Once they are extended to complex number, we notice that they are doubly periodic and they're also multi-valued. So we realize that the right setting for them are Riemann surfaces. And on Riemann surfaces, we generalize the notion of elliptic integral to abelian integral, and we generalize the notion of elliptic functions to abelian functions, which are just inverses of abelian integrals. Now, if you are interested in the details in this story, or if you want to know more about the intuition behind Jacobi or Abel's approaches, we covered those in other videos in this series. For now, thanks for watching, and let me know if you have any question.